It turns out that the Euler equation that we have just solved has a particular property. That means that its singular point is called regular. So this video is going to be devoted at looking into that section of regular singular points. First of all, let's visualize the solutions that the Euler equation has. I have attached a MATLAB code so you can look at it. This is a MATLAB code that constructs the solutions to the Euler equation. What I mean is not that it solves the Euler equation, it just constructs some basic building block that we have developed to see how the solution looks like. So the first solution that we have is x to the power r. The second solution that we have built is x to the power r times logarithm of x. Note how all the powers and multiplications have a dot in front because I'm going to be using x as a vector, so I want everything to work correctly. Then we have f3 and f4 that are the solutions for complex roots. So we have x to the power lambda times sine or cosine of mu at logarithm of x. We're taking x roughly between 0 and 2, and we're going to plot that there are some lines to discuss about how I want things to be plotted, but the core information is here. We plot x with respect to f1 computed at x with a power I. So I'm looping, having a for loop for I going from -3 to 3 to see how the plot changes when I change the coefficient of x, the power of x. I put a title and I put a legend. In the second figure, I do something very similar. I put a title that is repeated roots, and I do the same loop and the same type of plot with the second type of base function that the Euler equation has. That is the one we saw before, x to the r times log of x. And the third figure is a bit more complicated because for complex roots, I have both the sine option or the cosine option. I chose to have lambda equal to 1 all the time because I noticed that if I was plotting more powers of x, it would be complicated. And then I'm changing mu. That is the coefficient within our sine and cosine. With a legend, a title, just to distinguish the various plots that we're having. So for the case of the distinct roots, then we have the case of the repeated roots. There is a warning that pops up and I don't understand why, but I'm not going to look at it. So we have figure 1 that shows how the distinct roots give us different powers of r. So if you look at the legend, we go from, I hope you can see it in the video, it's kind of tiny. We have r at the -3, that is this function here that goes down fairly steeply. Then r at the -1, r at the -2, r at the power 0, and then the positive powers. R at the power 1, r at the power 2, the cyan one, and r at the power 3. They all cross at 1, 1. For the figure 2, we have cases with repeated roots. So for repeated roots, we have x to the power r times logarithm of x. Logarithm of x is -infinity for x tending to 0. So for problematic values of the power of x, so for negative values, you see that things are tending to minus infinity very fast. Because logarithm is tending to minus infinity, and 1 over x to the power 2 or 3 or 1 is also tending at infinity. So it's going down steeply. While for x at a positive power, then the power of x takes it over the logarithm, and at 0 we tend at 0. Then they all cross here, again, at logarithm of x equal to 0 for x equal to 1, and then they branch off to plus infinity. Well, positive powers of x go to plus infinity, negative powers of x go to 0. So this is the wiggle you're going to see for the repeated roots of the Euler equation. Then the last case is the complex roots. We have a combination of sine and cosine, multiplied in this case by a power lambda equals to 1. So we're multiplying by x. We have sine and cosine of something, and sine and cosine oscillate between 0 and 1, so they're bounded, multiplied by a power of x. So you see that everything is bounded by minus x and plus x. Within that, you see oscillations depending on the mu. So we have sine of mu times logarithm of x and cosine of mu times logarithm of x. At 1, you see how all the sines tend to 0, because logarithm of 1 is equal to 0, and all the cosine tend to 1. And at 0, we have the logarithm tending to minus infinity, but sine and cosine of something that tends to infinity is still bounded. So we're seeing, if you would zoom in and if you would be able to plot it, you would see many, many oscillations going very fast in here. And then they slow down and become slower and broader because of the multiplication by x, away from 1. So these are the different cases of solutions of the Euler equation. Having seen the different types of solutions to the Euler equation, let's look at regular singular points. As we have seen in the Euler equation, when we look at x squared y second plus alpha x y prime plus beta y equal to 0, x equal to 0 is a singular point. It's terrible. Sometimes the solution doesn't even exist at x equal to 0. When we're taking logarithms of x tending to 0, we have a huge problem. So obviously we cannot use power series to solve for the Euler equation. It would fail in the cases in which a solution doesn't even exist. But we still were able to find solutions. So we wonder if maybe for the case of the Euler equation at x equal to 0, we're in a case in which the singular point is nice enough. And actually that's true. We introduced the concept of regular singular point for this idea. We said that x naught is a singular point if p of x naught is equal to 0. Because if we are trying to make x, the coefficient of y second equal to 1, and we are dividing everything by capital P of x, if capital P of x naught is equal to 0, we have a problem at x equal to x naught. But we try to contain the problem. We say that if the limit for x tending to x0 of capital Q x divided by capital Px multiplied by x minus x naught is finite. And a similar thing holds for x, that is the limit for x tending to x naught of capital Rx divided by Px times x minus x naught squared is finite. So if both these limits are finite, x naught is a regular singular point. The Euler equation fits this perfectly. We have that P is x squared, Q is x, so x divided x squared gives you 1 over x, and you add an x in front, so the first limit is equal to 1 to alpha, and the second limit is equal to beta. So in both cases, we are in the finite case. So x equal to 0 for the Euler equation is a regular singular point. And that means that for regular singular points, next week we will see methods to solve them in a general setting. Let's look at an example classifying the singular points of this equation. So we have that px here is x minus 1 times x minus 3 at the third, qx is x minus 1, and rx is x minus 3. Can we classify all the singular points in this equation? So first of all, the singular points in here are x equal to 1 and x equal to 3. Then we have to compute the limits that we just defined. So for the first singular point, x equal to 1, x naught equal to 1, we want to compute the limit for x tending to x naught of x minus x naught q over p and x minus x naught squared r over p. And we do that, and we can do this, and we find that both limits are equal to 0, so x naught equal to 1 is a regular singular point. Let's try x naught equal to 3. So we have limit for x tending to x naught of x minus x naught q divided by p. A lot of things simplify, but what is left is limit for x tending to 3 of 1 divided x minus 3 squared. So it is not finite. X naught equal to 3 is an irregular singular point, and we don't even have to check the second limit.